Right, so I'm Neelan Marais, and my colleague Charles is also helping me present. And we're from SKA South Africa, and we do radio telescopes. Why radio telescopes? Well, simply you get to see a different part of the spectrum. On the left you can see an optical image, and on the right a zoomed in copy with a false color radio image of an interstellar hydrogen gas overlaid. And as you can see, you can't see that on the optical image at all, so that's pretty neat. For more details, you should go and look up a video of a talk Simon Ratcliffe gave yesterday, if it's online. So an optical telescope kind of looks like this. Light is collected by a large mirror, and then it's focused. Can I point to this? Timer? No. Oh, maybe this works. Right. So you can see there's a mirror. It reflects it onto a sensor, and it's kind of like your digital camera, only better. An optical telescope, a minimal radio telescope looks like this. Radio waves are collected by a parabolic reflector, and it's focused onto a receiving antenna with a low noise amplifier, and it's really a lot like your DSTV dish, just better. Right, it's much better. But a single dish is still a rather limited kind of instrument. It's almost like a single pixel camera. So what do? We use multiple dishes. So a typical modern, or a small typical radio telescope looks like this. Radio waves from multiple dishes are mathematically combined, and that allows you to image the radio frequency sky, letting us make images like one you saw in previous slides. Okay, so we do controller monitoring, Charles and I and our other controller monitoring team colleagues. And what we're dealing with a telescope which is essentially made up of a large number of distributed and fairly independent devices. So CAM is the nervous system that pulls it all together. And so the control bit is getting them all to work together to do what we want them to do. And the monitoring bit is receiving sensory feedback. They're like humans, they have sensors. And so from that we can identify unsafe or damaging situations and take action as needed. Like you can shut down stuff if it's overheating, or if the wind is blowing too strongly, you can put the antennas in a safe position. And we also monitor parameters that influence data quality. We also store the telemetry information, like the antenna positions, because the scientists later, when they process the data, will need to know exactly where the antennas were pointed at when the observation was made. And remote operation is very important for us. We like to keep stinky humans away from our telescope, because we do stuff that emits radio frequency interference, and that's our enemy. So network transparency is kind of an important thing, and that's also why we can give you a live demo today. Right, so what are we dealing with now? It's CAT 7. So CAT means Karoo Array Telescope, and 7 because, strangely enough, there are 7 dishes. It's a conventional prime focus design, which means that receptor antenna. Oh, sorry, that was meant to happen. Go back, please. Listen to me. Yes. So the receiving antenna is at the center of the antenna, as you can see. And what is unconventional is it uses a Stirling cryocooler to cool the low noise amplifier, and it's constructed out of composites. It started being built in about 2008. It's pretty much done now, and we're using it daily. However, its main job is to be a risk reduction kind of engineering prototype for Meerkat. So it's the hardware equivalent of release early, release often. It's also used for science, but that's a secondary goal. So we're working towards Meerkat. So it'll have 64 dishes, so more of everything. That's why it's Meer as in more cat. It's got a somewhat more advanced antenna design. You can see we call this feed low, because the feed's actually sitting close to the ground, which has a number of practical advantages. And there are also some performance advantages to this configuration. But the construction and the cryocooling is actually more conventional. What's also nifty about it will have a multi-band, maybe you can see it here, there's more than one feed antenna that can actually rotate in on a carousel to work with different frequency bands, which makes basically the instrument more capable of observing more different kinds of radio phenomena. Preliminary construction is already started, and it's expected actually to grow into SKA phase 1, which will be about 300 dishes. So let's look at a single receptor. When I say receptor, I mean the combination of a reflector, the receiving antenna, physical motion control, and a whole bunch of radio frequency components that you need to actually receive a signal. So it's not just an antenna, but we often call them antenna. Right. So at the focus, we have the receiver horn antenna, which is connected to a low noise amplifier, which is cryo-cooled. And the cryo-cooler has an ion pump, which is not from Star Trek. It actually just maintains the vacuum which you need inside the cryo-cooler. It's got a noise diode, which we actually use for calibration, and another radio frequency amplification stage. And inside the pedestal, we have a positioner, which actually moves the antenna. We have some more radio frequency stuff, and we have a radio frequency to optical transducer, which turns the electric signals into optical signals that we send along fiber optic to the central processing area. And this little block, I keep pressing the wrong button, but the little block at the base of the antenna is a chiller unit, which creates chilled water, which is used to keep everything cool. And there's also building management, which sounds kind of boring, but one important detail is that damn door has to be closed. Otherwise the radio frequency leaks out and it ruins the observation. And there's also close to the antenna is a weather station, which we use for monitoring the wind and stuff like that. So we have 7 receptors, so basically 7 of everything you saw in the previous slide. And yes, you might have seen this picture before. Okay, so those optical signals then all feed into the compute container. It's kind of a standard shipping container, but it's especially RFI shielded to keep all the radio frequency noise generated by our banks and banks of humming machinery inside. And it's kind of cool. It's got like airlock doors. You open the one door and then close it, and then the other one, so you can actually go in while we're observing. Yeah, so keeping RF in is important. So inside there's a whole bunch of cool stuff. This is not all of it. So let's see if I can show you this. You can't see it, but there's the RF to optical transducer, and then this thing basically, there's another rack at the bottom which is the same as the top, receives the analog signals from all the dishes, and it kind of mixes it down to a intermediate frequency, which is what we actually digitize. And then there's the FPGA based digital backend. So these are main component of our humming machinery. Inside are the biggest, baddest FPGA chips you can buy, and they crunch kind of a first level of number crunching. And here, and these ones also have the analog to digital converters, which are actually quite monster. And this is probably my favorite bit of equipment in the whole telescope. It's a atomic clock that's GPS disciplined, because time is incredibly important to astronomy and radio astronomy in particular, because you actually need coherent clock signals all through the system. So below it is a little NTP server, and below that is an oscillator which generates the 800 megahertz clock used for the analog to digital converters, but it's kind of synced to the atom clock, so it's very stable and very accurate. And there's again building management and a chiller. Right. So what are the principles of our controller monitoring system? So the most important thing is, as far as possible, everything speaks the same language. We have CAT-CP, which I'll talk about in the next slide. And we try and keep the things to be the system is kind of self-describing. We have a basic config, but then once that's set up, you can introspect the devices and see what they have and what they can do. Obviously, we don't expect them to change too often, but still it makes the software much simpler. And we use the idea of soft real-time. So, which is actually kind of why we can use Python. So for time-critical commands, for hard real-time operations, is left to the simple low-level devices. So soft real-time involves us sending those devices instructions along with future data timestamps, and then the device with a hard real-time capability applies the command at the timestamp we gave it. So that's also why it's very important for our time sources to be synchronized. But this simplifies CAM development significantly, because I don't know if anyone's ever done hard real-time programming, but it's crazy. You have to know what every instruction basically does. It's no way to live, according to me. And most of that is kind of outsourced anyway. Okay. Right, so Karoo Array Telescope Control Protocol, or CATCP, is really at the heart of our control system. It's we specify CATCP interfaces for all our devices, and when we can't get that, if a contractor doesn't want to do it or can't do it, we kind of add CATCP interfaces ourselves. And this allows us to use standard mechanisms to control and monitor everything. For instance, we use Ganglia to monitor our servers, but we export certain metrics as CATCP sensors, and then we can use the same mechanism as the antenna on a fire sensor that will send us an SMS if a disk runs low. So it just kind of unifies everything. CATCP is homegrown, as you might guess from the name, but some of our collaborating partners in the US are using it. We experimented with some things before, it didn't quite work out, which is why we went with our protocol. So basic ideas: use Ethernet as a field bus, which also precludes hard real-time operation. And it's a very simple line-oriented text protocol which runs over TCP sockets. I'll show you an example now. And the idea of device introspection is part of the standard, which is, I think, pretty important. And there's also this idea of a sensor that so the device can have sensors that exports temperatures or voltages or wind speeds or states. And there's mechanisms for subscribing to those sensors. Oh, right, so this is to remind you that I want to do a demo. Let me first show you the source code. So this is how you write a very simple CATCP server. We import some stuff, a server and cat types module from CATCP. And these decorators basically tell us what parameters. So the request basically tells us what parameters the request expects 2 floating point numbers, and it will return a floating point number. And then the actual function that implements it is quite simple. This sock is supposed to be a socket object which you're not supposed to touch. It really just identifies your connection. So it's quite simple. I'll get to the sensor now, but essentially you just return OK to tell it it's fine and the value that you want. And then we have a sensor which we use to count the number of times our request is called. So every time the request is called, you can see here we get the sensor, and you basically say the time it happened is now. The sensor is a nominal value, so the sensor is OK, and we increment it. So now this is the code. Now we get to run it, which is the exciting bit. I'm on localhost, so I can do this. Sorry, bit of housekeeping. Split the terminal. So now I'll run that simple server. What's it based? And it'll listen on port 8000. And you can telnet to it. Not if you're an idiot. And it gives you kind of a welcome message, and now you can ask it things. So a request always starts with a question mark, and a useful request is a help request, which tells you something about requests. So I can say request help, divide, and the parameters are space separated, and you get back that hash means it's an inform, which gives you extra information. And it's inform for the divide command, and that's the doc string we gave in Python comes in as a help command, as a help. And there at the end is an exclamation, which is a reply. So every request question mark has a reply exclamation. So basically we're always shouting at each other. And it tells us it's OK, and it returned us one help command. I can introspect the device by saying help. Now this is a long list, but basically you get the same kind of request inform. Oh no, this is not what I want to do. Please don't. There we go. So basically you get the same request inform lines for every request that the device has, and that's how you can introspect it. And you can also say sensor list. You get a list of all the sensors, and you remember we defined the one sensor, so there's only one. Oh, the other requests are added by the base class, so that's like basic things like what I'll show you now. Let's first run our request. It's divide, request 1, 2, and you'll note it actually uses floating point division because we had the cat type saying it should be a float. And now we want to monitor our sensor, so we can subscribe to the sensor by setting sensor strategy. Sensor was called no divides, and we want an event strategy. So event means whenever I still can't type after all these years. Right, so now every time we change that sensor, so if we run our request again, you see it, we get an inform line telling us that the sensor value is updated. So basically, in KCP you have requests which are essentially synchronous, and you have these kind of informs which can give you asynchronous information about what's going on the device. So typically you'll subscribe to a bunch of sensors and you just sit back and listen to them for monitoring. And it also gives us some free error handling, like if we do this, it'll tell us we need to give it some more parameters. Okay, so that's that. Now let's get back to the exciting stuff, which I won't be doing. Right. Okay, so back to the slides. Oh, sorry, this is where Impress is quite wonderful. You can't actually bring a slideshow to the front. I can't do it. So, apart from the basic CatCP devices, we use a thing called proxies. They sit between the devices and the users, and they basically shield the device from users. For instance, many of the devices are implemented as small kind of embedded processors, and they can only handle one concurrent connection, so the proxy makes it possible for multiple clients to talk to the device. And we can also hide or wrap certain functionality of a low-level device. For instance, the digital backend, those FPGAs have 16 channels. We only use 14. So the proxy can hide the sensors relating to the other two channels, so we don't get false alarms about signal levels. And we can also add higher level functionality. For instance, the basic antenna control unit only knows how to point an antenna relative to its kind of base. But what astronomers want to do is they want to track sources as they move through the sky. So the antenna proxy is connected to a database of astronomical sources, and then it will update the position of the antenna every 50 milliseconds, so it's very smoothly tracking the object through the sky. And similarly, you can use it to combine multiple small devices into a bigger one, which the antenna proxy, which we should call the receptor proxy, does. It combines all those devices I showed you initially that was on the receptor to look like it's just one device. Okay, and I think... Oh, right, so this is, I think, where Charles comes in, right? And I think I'm a minute early, so you have good time.
Okay. Okay. Let's click forward. Okay. Right. Okay. Well, Nilan's already mentioned the proxy layer. It protects the hardware from foolish humans. It also allows us to buffer commands if necessary, to aggregate sensors, and generally to turn a dumb hardware device into a slightly more intelligent software object that we can safely manipulate. We've also developed some higher-level interfaces. Obviously, doing everything through Telnet is not an option. So we've got some IPython libraries that make life significantly easier. And there's also a scripting interface for batch type operations. The whole system is designed for remote operation. It's been designed from the start so that it can be operated from Cape Town, and we do have people on site, but they are there for sort of local emergencies and for local maintenance and so on. The whole system is designed to be operated from essentially via the internet by astronomers anywhere, and maintenance can take place to a large extent from Cape Town as well. So, where are we? Sorry, there we go. Why do we monitor stuff? It's because the radio telescope is collecting this RF signal data, but it does need a bit more than that. You need a context for it, and the context includes things like where were the antennas pointing when you collected this data. Signals have to be combined and correlated, so we need to know exactly where all the dishes were pointing at every moment. There are also several corrections that need to be applied to the pointing information because of the distortion of the dishes, because of temperature and wind, also because of the actual antenna layout. There's a whole series of mathematical corrections that need to be applied, and the raw data, which is fed through to the science processing, is actually augmented on the fly with, well, sorry, not on the fly, but after the event with some this context information, so that it becomes possible to process it. Another reason for monitoring is that we need to be aware of equipment trends, we need to be aware of equipment failures, weather patterns, and I think Neil mentioned that if the wind speed exceeds a certain threshold, the antennas must be stowed, which is, I sometimes see them in a fully upright position. That's the safest configuration for them. We have a system of alarms which is activated when, for example, the temperatures of the equipment get too high. If the cryo cooler fails, then we need to know about that. Pedestal doors are left open, and, for example, if the radio frequency power levels become too high in the amplifiers, then we need to know, because that degrades signal quality. So we monitor quite a lot of stuff at the moment. On Cat 7, we've only got 7 dishes, and we monitor about 300 sensors at millisecond rates, and 100 sensors at second rates. Sorry, I think we seem to have a slight disconnect here. So it's approximately 260 sensors per antenna, and altogether 4,500 sensors at about 650 samples per second. That means that adds up to about a little less than 500 megs a day. And that's okay at the moment. We can store that information, but it's already getting to the point where it's a little bit annoying when you want to query historical data. It takes time to to read all that stuff, pass it across the network, and render it at a client. So we're looking at ways of dealing with that. Particularly as Meerkat is going to be 64 dishes, we're going to have more servers, more sensors per antenna, and a whole lot more samples per second. So we'll get the whole database is going to be growing at about 10 gigs per day, we think. So are we heading for trouble here? We need an archiving design that's going to be scalable and quite efficient, particularly for reading purposes. We think we have the writing covered, but reading is something that can be a little bit slow. So I just want to talk about the sensors a little bit. Those are as Neil said, they're the basic data gatherers. They're managed by a proxy, and it's a sensor. It's a software object, so we can do clever things with them. We can aggregate sensors into other sensors. We can average them over time. We can, and because it follows an observer pattern, so we just need to subscribe to a sensor in order to derive some useful information from it. For example, to activate an alarm when necessary. Sensors can have many types, and they communicate via CAT-CP. They can be float sensors, discrete sensors, Boolean sensors, or even string sensors, which are not generally sensors at all. They're simply a convenient way of storing some configuration information in a way that we can look up. Okay, and we're going to need a lot more of those for Meerkat. So, and of course the next thing is going to be, we're just looking at Cat7 in the slide there, I hope. Yep. SKA is going to have roughly 3,000 dishes ultimately. SKA phase 1 will only have about 300, but that's already becoming a challenge for our current architecture. One nice thing about our system is that the proxies and the sensors are self-describing, partly as a result of the CAT-CP protocol. So the system can actually configure itself dynamically. It greatly reduces the load for the burden of system configuration, because you simply tell it which proxies to connect to. The proxies tell you what sensors you have, and the sensors tell you what their names are and what they can do. And this makes for a very flexible, scalable system. So it makes. Sorry, we're getting to looking at what Meerkat is going to produce. It's going to be around about 5 gigabytes a day, and relational databases don't work terribly well with that kind of volume of data. At the moment, we've got a hybrid system. The index is stored in a relational database, but the actual data is stored in compressed files, a proprietary format, I suppose. But we are thinking about some other approaches. We are starting to look at PyTables, and our query performance is, as I said, just about acceptable for now. But we think it's going to get worse if we don't rework our architecture a little there. Okay, now to move on to something slightly different. Cat7 is producing science data, as you saw in that picture that Neelan showed, and in this one as well. This is good and interesting stuff, but Meerkat is going to be a far more powerful instrument. In fact, it's going to be easily the most powerful radio telescope in the southern hemisphere. So we expect a lot of interest from the astronomers. So there can be a lot of activities and observations running simultaneously. We need now, up till now, it's been pretty much an ad hoc process. You simply send a message to say, I'd like to use the antenna now, and you can reserve it that way. But with a bigger instrument and a lot more users, we need a framework that's going to control the access and allow concurrent activities while preventing accidental resource conflicts. So we have a thing called the observation framework. And the basic concept of the observation framework is schedule blocks. Schedule blocks are simply a way of structuring observations. They can be observation type schedule blocks, which are scripted in Python. They can be manual, which is simply an IPython session. And they can be of maintenance type, which is just simply a way of reserving the hardware so that it doesn't accidentally get used for something else. The astronomers at present are used to just running the Python scripts, so we need to introduce the discipline of the schedule block, which will make it necessary to specify in advance what resources you're going to use. And they're also going to be an important part of our proposal management tool and the observation planning tool, which are also bits of necessary bureaucracy which are going to have to be introduced for Meerkat and particularly for SKA. So for observation framework components, we've got cat core lib, which contains the routines that allow you to build a cat host, which is cat host is just the high-level container, which is the top level for our software model. The cat host container then contains the proxies, and the proxies contain not only their own operations but also usually a whole lot of sensors. There's going to be a controller resource manager which starts and stops the proxies and validates the schedule blocks, and it also allocates. The resource manager component has the role of allocating resources and reserving them for use by a particular schedule block. The scheduler is going to manage a queue, and it's going to, as each schedule block becomes available and is duly validated, it'll be submitted to the executor. The executor runs the observation scripts. It's a slightly higher level controller. Well, what should I call it? It's an executor. It runs scripts. It collects the output. It makes the output available online during and after the schedule block is executed. Okay, I want to do a little IPython demo, just so that you could see what our... Okay, except here, I can't see it myself. Right. Yes. Yeah. Then I have to stand back here. Must be easier if I put it down here. Sure. Sorry, it's experimenting. Okay. What we're going to do here is we're just going to we have okay, I'm not totally familiar with what this script has done so far, but we're going to... Okay. All right. So what we're going to do is we're going to find a target in the catalog. So we could say target equals cat dot source. Sources. which happens to be the same source that you saw in that earlier slide with the radio image. Let's verify that we actually do have a target there. Okay. So now we need to set that target on an antenna. So we can go cat. That's a good idea. Okay. Okay, I'm slightly defeated by this Alt tab. Okay. There we go. Okay, those are our telescopes. They're currently all stowed. And what we hope will happen now is when we get track, then just the antenna that we're instructing to track will move. Right. So that's talking to the proxy. The antenna itself is too dumb to know what a target is. It only knows about azimuth and elevation. So we're talking to the proxy, and the proxy, as we mentioned, does know about targets. So now we the next thing is the antenna mode has to be set. Cute. And the brackets here, so a little squiffy. And I want to use round brackets. Apart from that, it's perfect. Hey! Alright, this is a real picture. Okay. Seems to have caused a panic on site. They're all rushing up to look at the antennas. And there it goes. Okay, and while we're doing that, we can go. Okay. Antenna. Sorry. Underscore ACS position. No, it's actually for antenna position. CS. Get. Stop that. Go away. Yep. ACS. Request ASM do. Okay, meanwhile the sorry? P. So, sorry, being mad here. Okay, I seem to have lost focus. Yes, it's probably a better idea. Sorry, Q. print. Quotes around auto. Yeah. Well, strategy equals auto would do. Let's see. Okay. Yeah, I've got too many of them, but yeah. Okay, it's a little more manageable. As you can see, the azimuth and elevation do change in real time, and you can subscribe to these sensors and see what they're doing. Right. Meanwhile, that one has gone back to has reached its tracking position, so it's now moving very gently, but a little too slowly for us to notice. Okay, then finally, I would like to show you our GUI. Right, this is part of our graphical user interface. There's quite a lot more to it. Right now it's in manual mode. This is the scheduler. This is part of the observation framework that I was talking about. We have some observation schedule blocks ready here, which I need to show you. Okay, there's one. If one selects a schedule block, you can see the details over here. Okay, right now, if I put the scheduler into queue mode, then it will automatically queue that next schedule block, and we should see something happen there. So I'm going to do that. I'd very much like to move this so that one can see a little more of it. There we go. Yeah, sorry. Designed for big screens. Okay, that demo track is now active, and if we are quick, we can get over to the okay, can't see much happening there. Oh yes, okay, these guys are moving. Okay, the reason that the ant1 is not moving is that according to schedule blocks, ant1, sorry, that ant1 is this guy. I don't know if you can see my cursor. Yes, he's in maintenance mode. According to the fake schedule block that we've set up here, which means that the observation framework can't control it. It's assumed to be out of operation. However, the other ones are doing the business. Sorry? Except for the ones that are really in maintenance, yes, which we unfortunately we're not allowed to play with either. Okay, so we've now made all the other ones move. Next step was Okay, next step. Sorry. Let me get you back to our GUI. Okay. The way to get this antenna back to life is to take the take it out of maintenance mode. And find my cursor. Right. And done. Sorry, that is the... Is that the demo one? This one, yeah. Okay, so if we now... We need to... Sorry, there we go. Okay, we've got the right one now. Okay, because that's maintenance, all we need to do is say complete, and it becomes available to the system again. So that antenna is now available, which means that something else I've not shown you so far because of the it says it's ready as false because it's actually started running immediately. There we go. And here it is, swinging over to join its colleagues. Sorry, time's up. Okay, our time is up. I don't know if there are any questions, but I'm glad we got them to dance a bit.
Thank you, guys. There definitely will be questions. Here's some.
Thanks. What's the benefits of having the azimuth mounts over equatorial mounts with the antennas?
Sorry, the azimuth mount and
Over equatorial.
equatorial. It's simply that we have a lot of flexibility in positioning the antennas because the thing is entirely computer controlled. We can essentially do software controlled tracking. We don't need to have an equatorial mount, which is basically a mechanical way of aligning a telescope to the rotation of the Earth. A full Azel mount gives you complete control in all axes.
Once the it's how it was 75% of the SKA is going to be in South Africa and 25 in Australia. Are they going to function as a single unit, or
Probably not. A lot of that is still under discussion.
okay?
But the chances are that there will be some coordination certainly between them, but it's going to be rather difficult to.
Because the data mixing there would
And you want
be
to-
an absolute nightmare.
Yes. Yeah.
Actually, the SKA is right. It's actually like 3 or 4 separate instruments. So the most visible one is the one that will use dishes, and it will operate at kind of gigahertz frequencies, and then there'll be another instrument which operates at fairly low frequencies, like what you would use around for FM radio, and there'd be another one that's kind of in between. So those different frequency band instruments are actually pretty much completely independent instruments, and so the complete instruments will be either in South Africa or either in Australia.
So then your atomic clock would become quite important for knowing who would observe what at what time if you wanted to use those data sets concurrently
Yes.
in order to build up a more complex picture.
I think it's essentially impractical to use data sets collected in Australia and in South Africa concurrently. If you want to comment on that. Go on.
Actually, they do that already. It's called very long baseline interferometry, where they will have antennas that are thousands of kilometers apart, but it's actually, you need to be much more careful to get it to work. firstly, so they need very accurate time sources, which the atom clocks are. But they also, you kind of calibrate your instrument against well-known targets. So you'll do an observation with the two different antennas of a known source and then your actual target. And because you know what the known source looks like, you can fine-tune the delays and whatever between different countries. But coming back to the SKA thing, that won't be an issue here. We won't. You really can't use those different telescopes together because it's like you can't use an infrared camera together with a visible light camera at the same time. It's like it's two separate things, right? So you draw one picture for one and another picture with the other, and you can overlay the images later, but you don't. So by the time you get to that point, you actually know exactly where everything is. So that's.
Thank you, guys. Unfortunately, I need to stop you. Thank you very much for the talk, and I think some people will probably be contacting you in the passageways to ask you about making them dance. I think that should be the demo you do, like a sort of audio to dancing, of them dancing.
I think you can play a full-time
So actually, let's just show you can go to www.ska.ac, like academic.za, and there you'll find a link to actually a very nice time-lapse video of, it's called Cat 7 Dancing the Night Away or something like that. So.
Cool. Thank you, guys.